time to start doing some problems, but well, anyway. We've seen many of these things earlier today, so I hope we can just highlight the main aspects here. So, what do we have? Let's look at our data. So, there is a countercurrent process containing 3 stages. So, let's start by having a nice diagram of our process with 3 stages, and we know this is countercurrent. Right. So there is says it is designed to operate with that volumetric flow rate ratio aqueous to organic 5 to 12. What is that in our nomenclature? H over L, so that is 5 over 12. So we will have here H, we will have X, no? Okay. Right. What else do we know? Well, we want to find the percentage recovery of the solute A in the solvent, and it's the contamination factor from a trace solute B. So basically what we will have is a mixture then of A and B here. Okay. We know what the feed is, so 100 grams of A per liter, so this is 100 grams per liter. Do you agree with me that that is the input, right? So the aqueous feed contains 100 grams of A per liter and 1 curie of B per liter. So one is measured as mass, the other as radioactivity, but you know that those can be related. So we will have here L, and what else do we know? The solvent field contains no solutes. What information is that giving me?
0.
What's 0? Y4 is 0. Okay? Right. Do I have any other piece of data there? Well, I know what the distribution coefficient M is. So how do you write YA as a function of XA? So this is XA to the minus 0.5. Okay, yes, MAXA. So what is it? So what happens when you multiply this by XA? Is that it? Do you agree with that?
Which units are for what is equivalence in grams of the...
What do you mean? So we are going to work in grams per liter for A.
Yeah, but for B the units are curies per liter. What is the equivalent of...
It's a radioactivity unit. So, well, I don't know. I need to know what's the radioactivity of B per gram is if I wanted to compare, but we can solve this. Basically, the radioactivity will be proportional to the mass. So we can solve it we can use it as if it were a unit of mass. That's what we are. Okay. So do you agree that this is the equilibrium for A? So we also have a value for B. So how do you write YB as a function of XB? Come on, a last effort before the weekend.
E to the power of the right-hand side.
All right. So we have to write M, which is E to 1 minus XA. Sorry, this is XA over 20. And what else? Is that all? XB. Right? So let's look at this problem. So we have H over L will be related to our operating line. Okay, it will be the slope of the operating line. Is the operating line the same for both? Yes. A and B have the same operating slope because, well, they are in the same solutions and they are in contact with the same solvent, so this is the same problem. A, well, it's not a linear relationship between YA and XA, but this depends only on A, whereas for B, the equilibrium depends on the concentration of A, right? So the proportionality between YB and XB depends on A. So this is an important fact here. How much B is transferred from one phase to the other depends on how much A is in the system. So what part of the problem will you tackle first? The recovery of A or the contamination factor from B? So you can see here the decontamination factor B. What is the recovery of A? How do you write how much A, what the fraction of A that is recovered as in the extract? Well, let's go through some definitions we've seen a while back. So you remember that the loss is, well, that is for one stage. In this case, the loss will be related to what we have here, XA3, XB3. So the loss of A would be XA3 divided by XA0. That's the loss, that's what was not extracted. And how about the recovery? Well, the recovery will be what I extracted, which is L times Y1. So this is all the A. So this would be A1 over all the X I had already. Does it make sense? So the A that I recover in the extract is the A in the extract. So it's at that point there. The A I have in that strip there. Divided by all the A that I had as an input to the system, which is over there. So let's write that down. This is going to be valid for, of course, A and of course for B as well. So yeah, at every stage we will have A and B. So I'm just going to write the general definitions, then we'll have this for A and B. So this will be Y3 and this will be Y2. Okay. So can we calculate the recovery? What do we need to know? What is unknown here? Yes, because this will be 5 over 12 YA1 over 100. That was 100, wasn't it? Over there, that's 100. Excellent. Okay, so if we know YA1, we can calculate the recovery. How do we calculate that? Well, let's look into this. I'll leave this definition for later. Well, first, there are, if you remember, there are 3 ways we could solve this problem. First, there is this Spencer-Saunders-Brown equation. Can we apply it? No, why not?
Because it is not constant.
Yes, if you go back to how this equation was developed, there were some constraints on it. What were the constraints? Let's review all of them.
Constant flow.
Constant M, yeah, so we lost. We're out of the game because we didn't have a constant M. What were the others?
Constant flow rate. Constant flow rate.
Constant flow rate, that's right. So that's, yeah, we have that. That's our normal assumption anyway, so it's unlikely that we don't have a constant L or an A. There was another one which is, and this is important, don't forget this one, which is this equation is valid if this is 0, right? So that would not rule out this equation here, but if this input is not pure solvent, then you end up with another equation which contains how much solvent you are inputting. Remember that this comes from the mass balance, so this assumes that all the A comes on this strip. Well, there is an obvious one which E cannot be 1, in which case the equation simplifies to something else, but if E is 1, then you get an indetermination. But we cannot use it because, as you rightly said, this is for constant M and we have a variable M there. So we have to think what else to do. What else can we do? Well, we can solve it either graphically or by writing mass balances and equilibrium equations. And I'm going to do a combination of both, right? But just to illustrate the problem, do you agree with me that this is what defines our problem now? So we have an equilibrium line, which is not a straight line, as you see here. And we know the slope of the operating line, but again, as we've seen earlier today, do we know any point here? Do we know any point to be able to decide which of the infinite straight lines with the same slope is the one we are looking for? No. So, because remember that this corresponds to points, each of them corresponds to points in the cross-section. Here I know XA is 100, but I don't know Y1. Here I don't know either, same as here, X2 and Y3. And at this point, well, I know this is 0, so it will be, for example, that point there, but it could also be this point, or any point around here. So I don't know a point, I just know the slope. how do we solve this area?
Yes.
How did we do that? It was a bit of trial and error, wasn't it? So what do we need to do here? Well, we need to draw 3 stages here, 1, 2, 3, and at the end of the 3 stages, we need to be on this point. You agree with me?
Yeah.
Good. Now, I'm going to do a combination. Of course, you could solve it purely graphically, but let's see what is a reasonable starting point for our iteration. So we have to make an assumption first and see whether it holds. Making an assumption means to find what of these points would suit us, for example. So we need to pick one of these infinite curves, only 3 shown here. And for that, what is the value of y here? Because I know the x is 100. I have to assume what in other terms, if we look at that diagram. A value for what? For y, 1. Right? So I'm going to assume a value for y1. Where to start? Well, in principle I have no idea. So let's do some basic calculation. So that is what we want. We need to find in what curve this happens. Right? After 3 stages, we are at this point where y is. What is the maximum possible concentration in the organic phase? Well, that would be if all A is transferred to the organic phase. And this would be it. Do you agree with me? So that is for a recovery of 100. So we have there that if we assume y1 is 41.67, then we are saying, well, we know that for that we will need infinite stages because that's recovering all here. So what I'm going to do is to assume something lower. I know it cannot be higher because I will be producing uranium from, or producing A from something else. So I'm going to assume it's 30 grams per liter. So if we do that, then we can calculate XA1. Right? So we have assumed YA1 at 30, and how can I calculate this value? How was this done? So this is my operating diagram. This is the equilibrium line. I'm just choosing a line here. So at this point, this is 100 and y is 30. So how do you find XA1?
From the equilibrium relationship.
From the equilibrium, yes. So we have assumed here 30, and therefore you can solve for XA, and that will give you 36, unless I made a mistake. So that comes from the equilibrium for the first stage, right? Graphically, you will go horizontally until you meet that, and then if you come down here, you will have 36.
Excuse me. Your equilibrium curve, is that the graph of 5x, 5 to the square root of x, 5 times the square root of x?
Yeah, it should be a plot of that.
So we don't have to guess. We can just put 100 for x.
Okay, yeah. That's a good point that I like to highlight. You can have two approaches. mass balance, one for each stage, and 3 equilibrium equations, again one for each stage. And if you do that, you have 6 equations, and 1, 2, 3, 4, 5, 6 variables. Right? So you have six equations and 6 variables. You can solve. Does that make sense? So your unknowns here are YA1, YA2, YA3, XA3, XA2, XA1. The rest, YA4 and XA0 are known. M is known, H over L is known, so you only have 6 variables. You have 6 equations, so you can do that. You don't need to guess.
But it is
But-
recommendable.
Yes, but it's a system which is first not linear, can be troublesome, but you can do it and it's right. The thing is, I like to highlight how else you could do it and link it with the diagram, basically. That's what I'm trying to do. What you cannot do is to take this 100 and plug it in this equation and find YA, because they are not at equilibrium. I mean, these two are not in equilibrium. I don't know if your question
That was the question.
Oh, okay, right. Sorry, yes. So you either do the system of equations and solve it, just pure math, or you guess and work with the graph, which is what we are doing. Those are right, but yeah, this string here is not in equilibrium with what comes out. The two in equilibrium are these two. The two that come from the same stage are in equilibrium, but the one going with the one coming. Right. So what's going to happen next? Now I know XA1, so I will write here what I think I know, because all this is based on an assumption which may or not be good. So how would I calculate the then the next step? So basically now I would like to calculate Y2. Graphically I know that it is going to be on the operating line. What if I want to calculate this? What would you use? So with the data I have, so I have assumed this is 30. Let's just write a warning on these numbers because they are based in assumptions. How do I calculate Y2? A mass balance. How do we do the mass balance? Mass balance for what? For stage 1. How do you write a mass balance for stage 1? Let's do that. Just to check that. So what are the input streams to stage 1? Well, we will have H times XA0. So H times 100 plus, so that's an input. What's the other input? Ly2. And that has to be equal to the output. What's the output? Okay, it would be H times 36, so this output here, plus L times 30, which is the output at this point. So if you divide by L, what you have is H over L times 100 plus Y2 is H over L times 36 plus 30. And H over L, I know what it is. This is 5 over 12. Is that right? Any questions? Is that, do you trust this mass balance? Right, again, what goes in here, h times 100, plus what goes in there, L times Y2, that's equal to h times 36, so this string here, plus L times 30. I don't know h and L individually, but I know h over L, so if I just divide by L, I know everything here apart from Y2. So I can get Y2. That's right. So this will be the value of Y2 if you solve that mass balance. Now, what happens next? Well, you would be at this point. So this is 3.33. How do you find the next point then? How do you find, what can you find next? What will be the next concentration to find?
We don't need to go further because we see that it's not going to be 3 stages.
Yeah, according to this diagram, it's not. Shall we check it with the balances? Because this, well, this heavily relies on how I do things. So how do you find x2, for example?
You can use that formula if it is in equilibrium, so you can take them up to its
Yes, x2 and y2 are in equilibrium. So
5 square root of x.
yes, you use that, and let me see what I got. I got 0.44. So now, if you want to go ahead, so this is the x2 that will be here, 0.44. Now, if we want to calculate y3, what will we do again? A mass balance, the same as here, but for stage 2. Do you agree with me? So, again, for stage 2, look, for stage 2 we have this input, these two outputs, we know them, so we only need, the only thing we need is to calculate y3. So we can do it with a mass balance. Are you convinced about that? No. Yeah, so you have 3 streams, you can calculate the 4th. Well, it doesn't work. It doesn't work not because you cannot write a mass balance, but because it will not close. You would need a negative concentration if you do the actual calculation here. Right? So this y3, shame I didn't have it there, but it will be minus something. So what went wrong?
The assumption.
My initial guess is wrong. If you want to see that graphically, as you pointed out, well, you can see from my graph over there that there was something wrong about this. Well, that is, if you continue, you could calculate that XA3 would be 28, but that doesn't make sense because we were already here at 0.44, so how can we go to 28 here? So this is all contradictory. And that is because our initial guess, that number 30 there, was wrong.
Wouldn't it be, I mean, this could be more time consuming as the system gets bigger and bigger. But we could stipulate initially that the operating line is simply a function of y equals x times 5 over 10. And then you can calculate, using this graphical method, what is what is y0, and you get something like 3 or something, you then use this value to calculate what the n should be to move the operating line. You move up again, and you have a discrepancy at
Yes.
x at x0, and you just do this 3 times, and things fit together.
Yes, it's a trial and error as well, so it's similar.
No, but I mean, the level of computation is much similar because it is much simpler. Because here you have to solve all sorts of equation systems, which gets difficult. But there you have one number inserted in the next equation, yet one number inserted in the same equation, and you repeat this over and over again.
Yes, as I said, I mean, you can solve the equation. You can even guess and solve it theoretically there or analytically. I'm just trying. The point here is just trying to make the link between the assumptions, which is basically what you are doing in the graph, with basically the assumption with what happens in the system. So our problem is that we selected a value which was here 30, and then after 2 stages we found that to close the mass balance at stage 2 we needed a negative concentration there. So of course that's not a solution. So our initial guess was wrong. Which way would you move for your next guess? Up. Yes. So we know it cannot be higher than that point because that's the equilibrium. That was if everything went to the organic phase. So it has to be something between 30 and this point, which was 41.67 or something. Right. So, well, you can assume something else and do the same thing. I'm not going to go to the details and have some problems in between. And then, in this case, the other problem you could have is that you overshoot. And so after 3 stages, you don't reach negative, but you don't reach 0 either. So
if we have this in the exam, are we ever going to get out?
Yes, the exam lasts 10 hours. And no, I mean, what I will be looking in the exam is that you know the procedure. It's not how good your first guess is. There may be not guess at all, because actually we're dealing here with the most difficult problems. But if you know the value you want, you will achieve here. So if you know the 2 values at a cross section, then there is no guess to do. Okay? Or for example, say if you are given the inlet condition and you are given the value you want to achieve here, then you don't need to guess. Basically, if you know 2 values at a cross section, then you know exactly what the operating line is, and there is no guess involved.
Wouldn't it be easier to solve the mass balance manually?
Hmm?
Wouldn't it be easier to solve the mass balance manually?
Yeah, well, depends. I cannot predict what will be in the exam, even if I wrote it. But look, the idea in the exam is not that you spend long hours trying to get the perfect solution. And imagine you are in the exam and you showed me twice that you know how to proceed with the diagram, and you didn't close it. Well, just leave it there. You get full marks anyway. You showed how to work with the diagram. It's not how good your guesses are, but how you know about it. Right. So if you make the right assumptions, then you can close it. So it was 40, and this is what happens, as we know. Is there any question about this? I will just spend another 2 minutes on the case for B, which I will show you how that will work. But is it clear how the procedure is? So again, there are 3 ways of solving this problem. The Kemser equation, which we couldn't apply because we didn't have a constant m. The writing the mass balance and the equilibrium and solving just mathematically system of 6 by 6 or whatever number of equations, or you can have the diagram, solve it graphically with a combination. Here we are going from mass balance to the diagram to put some numbers, but so basically a combination of the equilibrium equation, the mass balance, and the diagram. So those are the three ways of solving. Any questions? So let's see what happens to B, because we were asked to, well, that's a recovery. So in the end, we found that YA1 was 40. Now what happens to B? Because now we know all the values for A, right? We know for each stage what A is. Let me just correct, these were the wrong figures. Now we have the right one, so this is x1 is 64, xb is 25, and xa3 is 3.06. Okay? So we know this. We have other values here, that, so this was 40, and this is something that I don't care about. Now, as we know these values, we can calculate MB, the constant for B. Okay? So remember, this is M. This thing here was MB. And do you agree with me that as we have the concentration, we can calculate it? So, what would the diagram look like? Because we have a different M for each stage. So the diagram will be something like this. So now the equilibrium line is a different line for each stage. So this line corresponds to what stage? This is the equilibrium line for stage? For stage 1, where the concentration of A is 64, here. And similarly, stage 2, 25, stage 3, 3.06. Where is the inlet? What is our initial XB? Well, it will be 1 curie per liter. So this is our initial condition. What is missing on this diagram? The operating line, right? And we can now draw the operating line, which we know the slope. We will be in the same problem. This will not appear in the exam, by the way, so you can relax about this. But because here you will have to iterate as well, but I'd like to show you what happens to the system. So this is the right operating line. It was found after many days by iteration, so this is the definite diagram. But it's a slightly different diagram from what we see. So how do you find here YB1? How do you do that graphically? Just to look at the diagram. So we use all that information to build this diagram. This is the right diagram. I don't care how I found that this was the right operating line, but I did it. So I just want to show how this works. So where is that YA1?
Read it off.
YB1.
Read off the y-axis of 1 and then.
Okay, so 1 is my XB concentration. So at what point is YB1? So this is XB naught. This is 1. So what relates XB naught and YB naught? YB1, sorry. XB naught and YB1. They are on the operating line. So if I go vertically to the operating line, then that is where the value for YB1 will be. Do you agree? If this is the right operating line, then this has to be the value for YB1. So what happens, how do you calculate then? Now that you have yp1, how do you calculate the point here, xb1?
Now we see
The equilibrium line, obviously the equilibrium line for what stage? Which one? The bottom one. This is for stage 1, right? And this is an interesting thing. It goes up first, right? So this is the equilibrium for B at in this stage. So what happens next? How do you find YB2? Vertically and going where? Up to the red line, the operating line. And then, do you agree with me that then this is the point in the second, corresponding to the second stage? This is the equilibrium. And once you know, so this relates these two, and then you can find Y3 by coming down vertically to this point. And then you can find the conditions in the third equilibrium by going horizontally to the line corresponding to the last stage, to the third stage. And then when you come here vertically, well, you find that you meet the red line at 0. So this proves that this was the right operating line. And this is why I'm telling you that you will not find this problem in this way in the exam, because you will have to do all this iteration for different red lines until you find the right one, going back and forth. But what I like to highlight here is that this first transfer is in the opposite way. So you go with some concentration of B, and after the first stage the concentration went up. So it's an interesting thing that you can find, that because as the M is changing with A, the concentration could go up, but then it decreases. So after the stages, you end up with some extraction of B to the organic phase. In any case, in this case, as you wanted to have a separation, you didn't want that extraction. So with this, we solved the problem. The contamination factor. Then, if you say read off the values from the graph, will give you that value. So it's not a great process, not a great experiment. Well, there are previous past papers. There are problem sets on Blackboard, as you know. So feel free to drop me an email if you want me to. This is from the problem set, but it is a problem example. Perhaps even more complex.